Alrighty everyone, here we go. Today we are going to talk about force kinematics. So previously we had talked about vectors and linear kinematics and angular kinematics and how things move once they're moving through space, but we didn't talk about what causes these things to move in space, and so that's what we're going to look at now as we look at force and how it relates to kinematics. And here we go. Okay, a force. What is a force? A force is a push or pull that acts on one body or another. Okay, they are defined in one of three ways. It's either work, energy, or power. All of these are mechanical drivers that affect the body and are what we analyze when we look at the body as biomechanics. Man, you can really see. Definitely need a haircut. Sorry. One of the downsides of the coronavirus: no haircuts. So, let's dive into the first, right? When we look at work, what are we looking at? We're looking at an external force that acts on the acts on the given body. Okay, work is magnitude of a force times the displacement of the body. So work equals FP. Okay, remember P is displacement. The unit of measure is Newton meter, and that equals 1 joule. Okay, why is it a Newton meter and then why is it a joule? Okay, so force is typically measured in newtons, right? So we have a force, which is in newtons, times displacement, which is typically in meters, right? So everything's in meters when we're working in biomechanics. So you get a force times in newtons times a displacement, which is usually in meters, and you have a Newton meter once you get that equation right. So then 1 Newton meter equals 1 joule, and 1 joule is 1 Newton meter. Okay, it's mostly based off a measurement of torque. Is kind of how that works, and that's where that whole joule concept came from. So let's sit and let's look at work in terms of work in action. Okay, so the question is, how much work do I have to perform to lift my son off a counter to grab a towel from the cabinet? Okay, as we look at it, we're going to look at 3 phases of this motion. Okay, we're going to have the ascent, the hold as I hold them there. So the ascent's when I pick them up off the table. The hold is when I'm holding them there to pick out the towel, and then the descent is when I start to bring him back down after he's grabbed the towel and I bring him back down. Root beer gets you through. Aldi brand, even the best. So what we want to do now is pull up this whiteboard. So we have our whiteboard, and then let's go ahead and draw out our picture here. Marker, black. Okay, so we're going to say this is me. Here, sorry, I wanted that fat tip. Right. So I'm sitting here, I have my hands, both hands down, boom. There's my legs. I feel like the legs are long, but it's okay. Boom. Here's the counter, right there. Here's my cabinet, right here. Don't mind the dent, looks like someone bumped their head, right? Alright, so now as we have our hand, I'm on my diagram here. Here's our counter, right? We're gonna draw the object as a box, okay? Just because it's easier when we look at it in terms of a free body diagram, okay? If you ever need a whiteboard, I'm using this new website called Limnu, Limnu, free account. It's pretty good. So this is what we will call baby. Okay? So as we look at it from here, my current distance off the table right now, so as we lift this up, this is going to be the distance we're looking at. Okay? right now it's at 0. Okay, but as I lift it up, all it has is gravity pushing down on it. The table pushes back. We have nothing. All right, so as I lift it up, though, what's going to happen is I'm going to lift it up with a force of 100 newtons. Okay, and then this 0 will now change because I only need to lift him 0.2 meters off the ground or off the counter to reach the object, right? Then I'm going to hold him there. So we'll imagine that I'll draw this dotted box. Okay, and we'll say that's where it is when he's picked up. He grabs his towel. Excuse me. Grabs his towel, and then I will lower him again. Okay? Actually, that's wrong. That's a wrong depiction. I'm sorry. It'd be more beneficial because I'm still going to be putting a force upwards to resist gravity as it comes down. So my force will still be a positive 100 newtons. But what will happen is this will become a negative 2 meters as I return them down. Okay, so remember, you're like positive, negative, how does that happen? Right, remember that ultimately, right, what we have here is draw it as our x and y axis, right? So anything this way is a positive, anything this way is also positive, right? So as I'm moving up here, 100 newtons, positive. As I lift it up, positive in my distance as well. But then as I'm coming down, now it becomes a negative distance, okay? So what we're going to do now is move this over. So now you kind of have your visualization, but it's also beneficial to look at this in terms of a graph. Okay, not sure where that brown line came from there. I don't even know what that is. Okay, so we have this graph, and we're going to have a look here at what happens. So we start here at the counter. I pick up the child. I hit 2 meters off the ground, or 0.2 meters off the ground. I hold him. He grabs his towel, and then I bring him back down. Okay, so it really looks like that as if we were to look at this motion through a curve, and then we could divide it into 3 different parts, right? The ascent, the hold, and the descent. Okay, for ease of reference here, how's this look here? Remember that I moved 100 newtons is my force. Okay, I'm moving 0.2 meters, and that's my displacement. So a little p. Okay. So as we look at this and we try and determine how much work is being done, we have to look at it in 3 different phases. Okay. So we're going to look here at the first. We're going to look at ascent, right? Work equals force by displacement, right? So if we look at it under, I need to just sit back and stop leaning forward. You guys can see me. There you go. So as we look at it under the ascent, right, what's happening? I lift him up. I have 100 Newton force. So we have 100 newtons. And I'm going to multiply that by the 0.2 meters that I'm displacing it, right? Because I'm lifting him up 0.2 meters. So that's going to leave me with a 20 Newton meter, 20 Newton meters of work, or 20 joules of work. It just sounds better too. 20 Newton meters of work. You're like, what is that? Right? So now that's how much work we do in the ascent, and that is a positive number. As you notice, we don't have any negative numbers here because everything's moving up, right? So then we take that same equation. It's going to be 100 because it's F, right? My force at the hold phase is 100 Newton meters as I'm just maintaining that position. But what's my displacement, right? You see here that's flat. So I have 0. All right, so 100 times 0 equals 0 Newton meters, or 0 joules. Okay? And then at my descent, so I'm not actually doing any work here while my muscles are contracting and working. They are contracting. They're not actually doing work by the definition of biomechanics work, which is a force times a displacement. I have a force, but I have no displacement, thus I have no work actually being done. And then lastly, as we look at the descent phase of that curve, I have 100 newtons. And then I'm going in a negative 0.2 meters down. So that's going to give me a negative 20 Newton meters, or a negative 20 joules. Okay? So that's why we kind of break that down. So if we're looking at work of that motion of picking up a child, holding them, letting them pick a towel and down, or just picking up a box or picking up laundry, you could really do this for anything, right? That is how we would define how much work is actually being done. Okay? That's work equals force times displacement. So now what we're going to look at is energy. Okay? And there's two main sources of energy, and that is kinetic energy and potential energy. Potential energy will be further broken down, but kinetic energy is pretty much when energy is present in a moving body. So a body is moving, and then it makes contact with another body, and that's when that kinetic energy is typically released. Potential energy is an object has the potential to create a kinetic energy. Is almost the best way to think about it. Okay, so if you're looking at a bowling ball, if I have it sitting on the desk in a stationary position, it doesn't really have any potential energy, right? Because it's stationary, it's solid, it's not elevated, it's just sitting on the table. Okay, in regards to the table and the bowling ball, I would have to create a kinetic energy between my hand and the ball to push it to make it fall off and create it there. But that's more complex. But if we're looking at just the ball on the table, it has no potential energy. It's just sitting there. But if I pick that ball up off the table, now it's elevated, now it has a potential energy because now it's in a compromised position that if I drop that ball, it will hit the ground, releasing kinetic energy, and thus we would say it has now potential energy. You could also think of it as a rubber band. If I put a rubber band around my fingers like this, right? Sorry, like this. Okay, and it's not stretched. It's just around my fingers. Zero potential energy, because if I let go, it's just gonna fall to the ground. It's nothing, right? But, sorry, if I take that rubber band, put it on, and I spread my fingers wide, and I'm trying to figure out my camera, there you go, and I spread it wide, far as I can, right? And now I'm stretching that rubber band, and then I let it go. Now I have a pop. Now it's going to have some snap to it, and it's going to hurt, right? Because now I've stretched it, given it potential energy that if I just release, bam, kinetic energy released. Okay? And then remember that as we're looking at energy, just remember that no new energy is created in the universe, right? Energy is neither, it's like matter, like neither lost nor created. That'll come in handy at the end here. It's just transferred. Okay. Kinetic energy. Mathematically, what is it? It's 1/2 mass times velocity squared. Okay. So what does that mean? It means that the moving body has energy, and as velocity increases, kinetic energy increases. As mass increases, kinetic energy also increases, right? But if we look at the equation, which one is actually going to have a larger effect on our amount of kinetic energy? Okay, if my mass is going up and I increase my mass, I'm still taking half of that, right? Because it's 1/2 of the mass. So while I make small increments of that going up, I'm still taking half of that. So it's not as big of a factor, right? If I want to increase the amount of kinetic energy that I'm going to release, the most effective way would be to increase my velocity because that's a positive direction, right? And then I'm going to square that. Thus, I'm going to have a larger increase if I increase my velocity on something versus if I increase the mass. Okay? And that's kind of what we're saying here. Increased velocity has greater impact than a mass increase. Then we have potential energy. A potential energy is, like I said, the body has a potential to release energy, or release kinetic energy. It's best to think of it's the body is in a position to release the energy. The mathematical equation of that is potential energy equals mass times gravity times height. Okay? So we look at that, we increase mass, we're going to increase potential energy. We increase the gravitational pull. For us, that's not going to change. It's always 9.81 negative, right? Because it's going down, right? Gravity's always pulling down on us, so it's always negative 9.81. Mathematically, you could just, I don't care for our purposes if you use it in your final exam equations, right? If you're starting to look at arcs of like your broad jump or your high jump, right? If you look at that, I don't care if you just round it up to 10 to make the math easier. That's fine with me. And then our height, right? So if we increase our mass, we increase our height, we're going to increase our potential energy that we're going to have possibly released. There's two types of potential energy. Gravitational potential energy. Once again, that's mass times gravity times height, right? Pretty simple there in terms of that. The big thing is gravity on that bad boy. Strain energy. Okay, so now we're thinking about another type of potential energy. So let's move this bad boy over a little bit for us. It's already zoomed in enough, so just keep going over. Let's draw us a line. So imagine a, that's not working, there we go. A pole vault. Alright, pole vaulter is going to take a pole. It is straight, typically at rest. But as a pole vaulter, what I want to do is, if I'm here and I'm running and I'm pole vaulting, my goal is to bend our pole as I stick it into the ground to create a strain energy, strain potential energy here. Okay, so then the mathematical equation for that is 1/2 of K over delta, or 1/2 K delta x2. Okay, so what is that? 1/2 K is our stiffness, right? So I'm going to get far less bend on a 2x4 here than I would on a piece of PVC or fiberglass like poles and pole vaulting are made of, right? That's why they use that because they get more bend and they also have a greater strength by using fiberglass than they do if they just use PVC or wood or something like that. But either way, I'm going to take 1/2 of that stiffness and then I'm going to square the displacement, right? So the more I move the object, that's really what takes into effect here is the displacement. So if I moved our pole from up here to here and we moved it, you know, we'll say it's a 5 meter, not 5 meter, so it's a half a meter bend on that pole, then I'm going to square that. That's going to give me a much larger effect of 0.25 meters. 0.05, there we go, 0.25. That's going to give me a larger effect on my equation. Sorry, I got lost there in my thought. Right, because the further I move the object, since I'm squaring it, it's kind of like what we just talked about with our, where was it? Why can't I find what I was talking about? Our work, right? There it is, or kinetic energy, sorry. Our kinetic energy, 1/2 mass times velocity squared. If I increase the velocity, it's going to have a greater effect. Same with strain. If I increase my displacement, it's going to have a greater effect than if I increase or decrease the stiffness of an object. Okay? So now we get back into this conservation, not get back, but we re-mention it and revisit. Conservation of energy, okay? You have to remember that energy is not created. It is always present in some form or fashion, okay? So what that means is it bounces between the two is what we kind of think of it as, okay? So we have this kinetic energy plus potential energy equals total mechanical energy. Okay, so we're going to take an example of a vertical jump. I'm going to move this over so I can just write down my numbers here for it real fast that I used my example. 2 seconds. What I'm going to do is also going to make a discussion board. So if you guys have questions on any of this, I want to be able to answer it. Okay. I want to answer it, so, and I'll make a new video so you guys, we're nice and clear, all right? Because this is much better as a live presentation and in class where we can really look at this. But we have to do what we have to do, right? So my weight here, 40 kilograms, velocity, 6 meters per second, center of mass, 0.8, and total height. Oops. 1.8. Okay. Alright, so you see here, I've graphed it out. I have our weight here. Sorry, can't really tell. Weight, 40 kilograms. Velocity, 6 meters per second. I know, this is terrible already. Center of mass is 0.8 meters above the ground, and our total height of our jump is 1.8 meters. Okay, so we're going to assume that this here is 0.8. Okay, we jump up, and we come back down, ending again 0.8. Okay, there we go. What we're also going to have happen is this here. So let me go ahead and do this. What I should have done, actually, I should make this a different color. There we go. Fix that. Boom. Just imagine this is perfect, and I drew it right the first time. And then we'll give it a yellow. Nope. Let's go orange. And come back down. Boom, boom, boom. Imagine that's round, so that these are two equal curves, okay, in our world that we're doing here. So for us, this total height, let's do that in, let's go purple, okay? This total height here is going to be 1.8 meters, okay? This velocity here will be 6 meters per second, okay? So now, what we really want to know, or you guys are asking, is what are these curves, okay? This curve here, as you see, right, I said that energy is neither lost nor created, right? So what we have here, you see that as we jump off the ground, as little Billy here in pink is getting ready to jump. I guess I'll get his legs there. There we go. Getting ready to jump, right? He jumps up. What happens to his gravitational potential energy, right? So we have mass times gravity times height, right? Is gravitational potential energy. So as I'm jumping, I'm increasing what? My mass doesn't increase. Gravity doesn't increase. But what is increasing is my height, right? So I go from a center of mass of 0.8 to a center of mass of 1.8, right? So my height increases, thus my gravitational potential energy increases. As this comes up, I'm not accelerating anymore, so my velocity kind of peaks out and I stop accelerating and I hit 0 right at this point. 0. And this is where the whole thing changes, right? Kinetic energy is going down, you see, because I've released it as this goes up. And then as soon as I'm here, now we're coming back, right? So my gravitational potential energy has hit a maximum, and now it's coming down. And now it's decreasing my gravitational potential energy because my height is decreasing as I'm doing that. And then when I hit the ground, boom, I have a maximum impact here of kinetic energy. Kinetic energy, very high when I'm near or on the ground, right? So that's why that happens. Kinetic energy is being driven into the ground to create the force to go up, and then it lands and my gravitational potential energy turns into kinetic energy as I hit the ground again, okay? Now there's also one more little line here. This is our total mechanical energy line. And what is that again? That is our kinetic energy plus our gravitational potential energy. And that's kind of, so that's the sum of this force and this force, because as you see here, as this goes up, this goes down. As this goes up, that goes down. Thus, the energy is not being lost, it's just teeter-tottering between the two forces, or energy systems. So, as we look and try to solve for this, right, this is a value, so we can kind of look at that. So we have to solve for both of these, kinetic energy and gravitational potential energy. Okay? So let's start with kinetic. Equals 1/2 mass times velocity, and we're going to square that. Okay? 1/2 of our weight, which we determined was 40 kilograms, right? Times our velocity, which we said was 6 meters per second. We're going to square that. Okay? So what we have is kinetic energy equals 20 kilograms times 36 meters per second. Okay? And then kinetic energy will ultimately equal, so we have 36, multiply that by 20, 720. And that is joules. So we have 720 joules of kinetic energy. Okay? So let's go ahead and put that over here. $720. So then we do gravitational potential energy. This all will come full circle in a little bit here as we start looking at work, right? Because it'll help you with your final exam. Mass, gravity, height. Okay, GPE equals 40 times, like I said, we can do this before, so we're going to just do 10 just to make even numbers for us here. And then I think my height I said was 1.8 meters. Let me double check. Yep, 1.8 meters. Okay. So then, clear that out. We have 40 times 10, 400, multiply that by 0.8, 320. But don't forget, we did have a negative in there. In our 10, our gravity, right? Gravity's negative. So we're negative 320. So what happens here, we'll write it down here, 320 joules. Thus, our total mechanical energy within this equation is 320 and 720, right? So we're looking at 0, 4, 1040. 1040 joules, okay? 1040 joules of our total mechanical energy. And then it just really changes from here to here depending on where it is in the cycle, right? So as 720, as our kinetic energy is going down, we lose this, but our gravitational potential energy goes up. And then it swings back down. And so these two numbers are just going to teeter-totter like this, okay? So now we're going to dive into power. So if somebody or something is powerful, what is that? What are we saying? We're saying that they produce an X amount of work during an X amount of time. Okay? So if I do 25 push-ups in 10 seconds, I'm producing a solid amount of work than if I were to do 25 push-ups in 20 seconds, right? So I'm more powerful if I can do more push-ups in a shorter amount of time than I am if I can do the same amount of push-ups in a longer amount of time, okay? And that power is typically measured in watts, okay? 1 watt is equal to 1 joule. Refer back to picking up a baby from the counter, okay? So we're going to look at it in terms of if I did this in 1 second and if I did this in half a second, okay? So let's go back up here and we do 20, 0, 20, right? We'll just try and remember that. What we'll actually do is up here. 0, -20. These are all in joules. It's just going to be easier if I just delete this. I wish the eraser could be bigger. Like I said, I'm going to open a discussion board. Just kind of call it video questions. And if you're looking at it and you think you can answer it, it'd be better if you guys could answer each other, because then you guys can kind of help each other out. You guys can create a little group chat. How do I do this? How do I do that? And it'll help out your own understanding, because you can teach it, you know it. Okay, so that's kind of how we do it. And we're all not mathematicians, right? You guys saw me mess up the numbers in class the other day, right? That's why we have calculators nowadays. I don't care about all this. And like I said, a lot of this is going to be done on computers nowadays, to be honest. But we need to know what that operation is doing. And for us, this is really going to tie into what we're going to do as we analyze our video, right? We're at Lewis where we don't have these cool toys. So how do we make these adjustments on the fly? Okay. So we decided that power is equal to work over delta T, right? So here's how we can look at it. If we're looking at the ascent phase, I did 20 joules of work, right? Over, we'll say for this part, 1 second, 1 second, 1 second, over 1 second. Okay? So we take 20 divided by 1, and then what we have is P equals 20 watts. Right, so I did 20 watts of power during the ascent phase. Then if we take the same, right, P, we're looking at work, we have 0 over change in T, right, it's 1 second again. So we have P equals 0 work, right, because I'm doing 0 again, over change in T 1 second. So at this point I'm doing 0 work. So 0 watts of power. And then lastly, we would do the same as we do for equation 1, except now it's a negative 20 watts of power. Okay, so you can see how if I do that over 1 second, what happens there. But now, let's say, just for giggles, alright, let's say that it took me half a second. What happens for each section, right? So it only took me 1.5 seconds to do the whole thing. Henry's fast, moves quick. Alright, so now we have our work, which is 20 over a 0.5, and you see that we get a P of 40 watts. Right, so now I've doubled my power by decreasing my time. Okay, P would still equal 0 here. No power. And then here it would be a negative 40 again. Okay, so you can see how that changes. Now, what's kind of beneficial is that P can also be defined as work, force times displacement over velocity, right? Because velocity still gives us a displacement over time, which is already what we're looking at here. We're already looking at a change of time. And we look at the displacement, which is kind of work, which is force times displacement. So we're working at the same things, and they're kind of used interchangeably. So our P equals force times velocity, right? This links power to acceleration, demonstrating that an object with high power has a high acceleration. So if you have a high acceleration, you have a lot of power. You're able to move a lot of mass fast and efficiently in a given direction. Okay, so this is what's going to help us as we move forward into looking at our long jumps, right? Just look at this work energy relationship. Work is force times power, or force times displacement. Again, energy has the capacity to of a body, is the capacity of a body to work. When only gravity is acting, total mechanical energy is constant. And so we'll look at this like mountain climber here. Okay, this is the part where I kind of wanted to link it all together for you. Let me clear this board because it's not necessary anymore. Okay, I'm going to draw a new item here as we finish up here. So this is like for you guys, right? You guys are going to be analyzing your own videos, right? So we'll say I have a mountain climber here, and he's hanging on up here. Woo! Made it to the top, right? We'll say he is 100 meters up. Okay, we'll say he weighs about 70 kilograms, we'll say. So we know how tall he is and how high he is, right? I'm going to draw this. No, I'm not. I'm not going to draw anything yet. So I want to figure out his GPE, his gravitational potential energy, equals mass, gravity, height, right? So I know he's currently 70 kilos. He is, for math's sake, -10 is gravity, right? And then we know he's 100 meters high, right? Equals 70,000 joules, right? So I know that total force is 70,000, because right now he's got 0 kinetic energy as he's sitting up top. All of it's in that, right? So my total mechanical energy is 70,000 joules. Okay, but if I let go, boom, all that 70,000 is now going to be down here as it turns into kinetic energy when he splats on the ground, right? But what I may want to know is how fast he was going. What was his velocity, right? So this is where I would take kinetic energy and I look at that equation. Mass, 1/2, mass, velocity squared, right? So we're going to look at it, and that's going to equal 1/2 of 70 times velocity squared. But we don't know v, right? But we do know kinetic energy, which is 70,000, right? As he hits the ground here. And that's squared. So how do I get rid of that? I want to take the square root, boom. That's going to throw velocity on its own. Then we're going to have here half, so we double. So that's going to equal, hang on, let me rewrite that. So it'll be 2 square root. $70,000 over 70. Okay. So this is how you can solve for velocity, right? So as we're looking at it, we see that we have 140,000 square root over 70. So then what we have is a velocity of the square root of 2,000 equals a velocity of 44.7 meters per second. 44, there we go. And that's plus or minus, right? Because we can go up or we can go down, right? So how does this affect you, right? You can use the same equation when you're looking at your broad jump or your vertical jump from our videos and you're analyzing them, right? Because you go up, you hit that max, and then you're down. This is the same exact thing you guys just did in this mountain climber guy, right? It's half the curve, so we're just looking at the other half. We know how much we weigh. We know how high we got because we did the vertical, right? So we know at least our displacement of our center of gravity, right? So we may have started at 0.8, like we said in our example at the very beginning. We might have started 0.8 meters off the ground, and then I jumped so high that I was 1.8 meters off the ground, right? So I know how high I got. I just subtract those two. And then what I would have is, now I know that. I'll be able to do mass times gravity times height. I know how high I got. I know what gravity is. I know how much I weigh. I can come up with my gravity potential energy. I can then take that and say, okay, that would technically be my kinetic energy. As I come back down and hit the ground, that's going to all transfer from gravitational potential energy into kinetic energy, right? And then I can say this kinetic energy, 1/2 mass times velocity squared. I take the same equation here, and now I say, okay, how do I determine how fast I was actually moving? And now I know, okay, the reason I only jumped 0.4 meters was because my velocity was not high enough to get my mass off the ground in a powerful way. Okay? So that's why this is important here. And that's why the math part is important, because it helps us determine the unknown. We didn't take a velocity of how fast we jumped. We only know how high, how tall, all these other variables. Okay? So that's what we're talking about here as we look at power and how these factors all tie in to the vectors that you're seeing and the motions. Okay? And that is it there. Okay, so once again, I said I'm going to post a discussion board. You guys can feel free to ask questions in there. No questions or dumb questions. I want you guys to just understand it. Just figure it out. Just figure it out. Understand it. Watch other videos if you need to. Read the Hamill book if you need to. If not, we'll find a way for you guys to understand this. So shoot me an email if you want to do office hours to be like, all right, I don't understand this part, right? And we can kind of figure it out. If we have a bunch of people asking the same kind of questions, we can figure this out from there. Okay, Thursday is when our class is scheduled, but that is Easter break, so I'll be posting. I posted a link for a seminar. I believe that is on Tuesday. I think it's the 7th is when that one is, or maybe it's the 8th. It's in Blackboard under the announcements on a video I want you guys to watch. It's about like the broad jump with a prosthesis, so it kind of looks at how you guys can analyze that as we go into looking at your final exam and how you're going to analyze your broad jump. Yes, you don't have prosthesis, but it's the same kind of principles, okay? They'll just look at more like biomechanical deviations as we look at that. And then I'm probably going to post one more video up throughout the week. Yes, we're on break, but you guys can watch it a little bit too. Hopefully I'll have it up before Thursday, since that is our class day, but we, like I said, are on Easter break. You guys look for a great snack right here. Get you through. Starburst jelly beans, only available at Easter. Gets it going. Alright. That's what we're talking about. Other than that, enjoy your Easter break. Enjoy class. Ask questions if you have them. Everyone should have the group presentations up. And I'll see all, for my Tiger King fans, all you crazy cat and kittens out there. I'll see y'all later.